Hello everyone, this is Group Neon and my name is Erin. Today, our group will talk about a problem that involves the equipartition theorem. In classical mechanics, equipartition or equal division theorem can be used to predict the contribution of each mode of motion of a molecule to the total energy of a collection of non-interacting molecules. The general concept of equipartition theorem states that the energy is shared equally amongst all the energetically accessible degrees of freedom of a system once it has reached the thermal equilibrium. The assigned problem to our group is problem 2A.1b, which asks to use the equipartition theorem to estimate the molar internal energy relative to the internal energy of zero for the gas phase at 25 degrees Celsius for iodine, methane, and ethane. But before we show you how to solve the problem, here is Kyle to give you a brief background of theory of equipartition theorem.
This is Kyle Josephson, and I'll be introducing the equipartition theorem theory and background. The equipartition theorem states for a sample at thermal equilibrium that the average value of each quadratic contribution to the energy is 1/2 times kb times t. In 3 dimensions, a molecule or atom has the ability to move its center of mass through space in the x, y, and z directions. This is referred to as translational motion, and each motional degree of freedom adds 1/2 kbt for a total of 3/2 kbt. An atom or molecule also has the ability to rotate about its center of mass, referred to as rotational motion. Each motional degree of freedom for rotational motion adds an additional 1/2 kbt. Vibrational energy, which includes kinetic and potential, contributes an additional 1/2 kbt. However, this is only taken into account at higher temperatures, such as those above 25 degrees Celsius.
Hello everyone, my name is Nathaniel, and I'm going to be walking you through Wendy and myself's solution to our problem. So in the problem statement, we are asked to estimate the molar internal energy using the equipartition theorem of 3 molecules in the gas phase at 25 degrees Celsius. The molar internal energy at low temperatures, such as the target temperature of 25 degrees Celsius, is equal to only the energy contributions from the molecule's translational and rotational degrees of freedom, plus the molar internal energy at t equal to 0. The energy contribution from the translational degree of freedom is the same for all 3 molecules, because we're in 3D, and from the equipartition theorem, we know that it's 1/2 RT of energy per dimension. So that's 3 dimensions gives us 3/2 RT. And the energy contribution from the rotational degree of freedom is V sub r over 2 divided times RT, in which V sub r is the molecule's rotational degree of freedom. For linear molecules such as iodine, V sub r is equal to 2, and for non-linear molecules such as methane and ethane, V sub r is equal to 3. And I can go into more detail in the next slide about those. For the final equation, molar internal energy at T is equal to the molar internal energy at T equal to 0 plus the energy contribution from translation and the energy contribution from rotation. So as we can see in the bottom left, the linear rotational degrees of freedom is equal to 2. That molecule can rotate in its x and y axis. And the nonlinear molecule that looks like water here on the right hand side, we can see that it rotates in all 3 dimensions, giving a 3 rotational degrees of freedom. Getting into the solutions now for A, we know it's 3 translational degrees of freedom, 2 rotational degrees of freedom because it's linear, and our vibrational degrees of freedom is 0 at low temperatures of 25 degrees Celsius. We can see that the molar internal energy is equal to the molar internal energy at T equal to 0 plus 5/2 RT, which comes out to 6.194 kilojoules per mole relative to molar internal energy at T equal to 0. In part B, for methane, it's a nonlinear molecule, so it increases our rotational degrees of freedom by 1, but other than that it's virtually the same. So we have 6/2 RT, which comes out to 7.433 kilojoules per mole. And in part C, for methane, again it's a nonlinear molecule, just like methane. 3 translational degrees of freedom, 3 rotational degrees of freedom. Our internal molar energy is equal to the internal molar energy at T equal to 0 plus 6/2 RT, and that's equal to 7.433 kilojoules per mole relative to the molar internal energy at T equal to 0. I hope that was clear, and if you have any questions, please feel free to ask.
In conclusion, the question asked us to estimate the molar internal energy of the system in joules per mole using the Equipartition theorem. We used the equation U sub n of T equals U sub n of 0 plus 3/2 RT plus V sub R over 2 RT to determine this value, which sums up the internal energies at T equal to 0, and the internal energy contributions of the motion derived from the Equipartition theorem. The results show that for the linear molecule of iodine, the energy contribution relative to U sub n 0 is lower than that of the nonlinear molecules. The simplicity of its 180-degree bond geometry allows for only 2 rotational degrees of freedom, limiting its potential energy. For nonlinear molecules, CH4 and C2H6, the energy contributions are equal because the energy contributions from the transitional rotational are equal at low temperature, and the energy contribution from vibrational degrees of freedom, which would change their molar internal energy significantly, are not considered.